Hello and welcome to this video on Cisco Wireless. No configuration in this video. I would like to look at channelization, look at 802.11g, A, N, and AC, and look at how the channels are set. There is an urban legend that says that if you double the channel width, from 20 to 40 MHz to 80 to 160, you simply double the throughput at any given location, and that's not true. And I would like to show you why, because this affects the performances of your devices and also the design of your cell. So I'm going to assume that you know that 802.11g, A, N, and AC all use a technology called OFDM. If you do not know what OFDM is, there are some other videos around there explaining to you the difference between DSSS and OFDM. And I'm also going to assume that you know that for 11N and 11AC, you can expand your channel size from 20 MHz to 40 MHz for 11N and then to 80 MHz and 160 MHz for 11AC. And for these two technologies, you can use multiple input, multiple output, which is MIMO, and send more than one signal at the same time. The principle behind OFDM is that you're going to take your 20 MHz wide channel, and instead of sending one large wave like you would do with the SSS, which is 802.11 or 802.11b, you're going to divide your 20 MHz into 64 smaller waves. So again, this is very different from the SSS, because in the SSS you're going to occupy 22 MHz wide bandwidth, and over these 22 MHz you're going to send one big wave that may contain some variations in signal intensity, and that's how you will be coding zeros and ones, but there's one wave. Whereas with OFDM, you take a smaller chunk of the channel, in that case 20 MHz, and you divide those 20 into 64 small waves. And practically speaking, they are independent, these waves. They are orthogonal, which means that when one wave is at its top, its max strength, max intensity, the one just next to it is just starting. This way they are not stepping on each other, so to speak. So they are sent next to one another in a sort of alternate fashion in the wave strength that makes that when one is strong, its neighbor is weak, to avoid collisions. So 64 waves, and if you look at 802.11g or 802.11a, those 64 waves are divided as you see on the slide. Namely, you take the first 6 at the bottom of the 20 MHz, and those you're going to not send anything, they are going to be flat. You also take the 5 top, and those also are going to be flat. This is interesting to isolate one channel from the other. So if you have two access points on two neighboring channels next to each other, say for example one AP on channel 36 and the neighbor on channel 40, these flat subcarriers, as we call them, at the bottom and the top allow you to increase the chance of non-overlap between the two channels. Of course, there is always a chance that your emitter or receiver is not perfectly aligned in its frequency, so there may be a drift a little bit of those channels up and down. So there still is a tiny risk of overlap, but it's more limited by nulling, as we say, putting to zero those channels at the top and the bottom. For the same alignment reason, the one channel that is right in the middle of the 20 MHz is also flat, no signal there. This allows the receiver to align its radio to the bottom, to the top, and the middle, and thus make sure that it's really carefully reading each individual of the other channels, which are carrying data. So out of the 64 channels with B and A and what we call legacy mode in 11N, 12 channels are null, 6 at the bottom, 5 at the top, 1 in the middle. 48 are active, that is to say sending traffic. And out of these 48, the ones you see in red, we have 4 of those. They are called guides or pilots. And what they do is that they do not carry traffic, they send a well-known sequence of signal. It's a pattern that keeps repeating itself over and over again. And the reason for those is that there may be some interferences or noise in the channel. By using those pilots, we send a sequence of well-known signals that the receiver is going to read and evaluate. And the receiver is going to compare what this receiver is receiving to what it knows that those channels should be sending. And if there is any difference, well, the difference is the noise on the channel. So this is useful because then the receiver is going to be able to apply the same noise figure and remove it, deduce it from the signals received in the neighboring blue channels that you see on the screen. Because interferences can be slightly different from one part of the channel to the next one, that's why we have 4 pilots. Each of them will be a sort of guide for the noise figure in the neighboring frequencies, and the receiver is going to deduce the same noise figure for all the neighboring blue channels. So pilots are very useful because that's how you get a clean communication on the neighboring blue subcarriers, because you're able to know what the noise is in this environment and remove it before you process the signal. But of course, they are not useful for data traffic. So if you look at this figure, we have 4 pilots out of 48 tones or subcarriers, and therefore we're using or losing 8% of throughput capacity to make sure that we understand the channel. When you move from 802.11g or 11a to 802.11n traditional transmission, not what they call the legacy mode, but the real standard 802.11 communication, we still have those pilots. The only difference really is that we move from 48 useful subcarriers to 52 useful subcarriers by basically only flattening out 4 channels at the bottom instead of 6 and 3 at the top instead of 5. So right there, by just using a tiny larger amount of channels or subcarriers in your communication, you go faster than with 11G and A. And this is why, for example, the bottom speed for 11G and A is 6 megabit per second, but the bottom speed for 11N is 6.5 megabit per second with the same modulation. And this is because we use a tiny larger amount of channels. We still have these 4 pilots, but now they represent 7% of the channels because we have more channels, 52 instead of 48. What happens if you change from 20 MHz to 40 MHz communication? Well, in theory, you take two 20 MHz channels, you stick them one to each other, and voila, you have a 40 MHz wide channel. Practically speaking, what happens is that your flat channels, your null channels at the top and the bottom stay here, but we go back to the scheme of using 6 of them at the bottom and 5 at the top. We're going away from the 4+3 that we had with a standard 11N on 20 MHz. We go back to the G/A type of model. But then as you see at the plus location, we have the top of one channel on one side and the bottom of the other channel on the other side. We don't need that many null channels on what will now be the middle of the frequency. So we're going to use only 3 null channels here, and of course we can get rid of those null channels in the middle of my previous 20 MHz because now these are right in the transmission mode, so we don't need those for alignment. So we use the one at the top to avoid overlap, just like the one at the bottom, with the neighboring channels, and then we use these 3 at the middle for calibration and identify the middle of the frequency range. What about the pilots? Well, if you count them, we had 4 plus 4 before. And of course there is a drawback. When you increase the channel size, you can say if I keep 4 on each side, then I still have the same accuracy in detection of the noise figure, but at the same time I'm using a lot of channels just for that detection. So there is a temptation to reduce the number of pilots to something smaller. And this is what was done with 11N and AC for 40 MHz. We move from 4 channels on each side to only 3 channels, 3 pilot, 3 guides. So at the bottom you see in red the new pilot location, and what you see in blue is the previous location of those pilots in 20 MHz. So in 40 MHz, not only we reuse more subcarriers in the middle here, and also we drop the null here that we use for data now, but we also remove the need for 4 carriers at the bottom and 4 at the top, and we go down to 6. All this together means that your 6 pilots represent 5% of all the channels on this 40 MHz transmission. And this alone allows you to also increase the amount of data that you send, because now we have channels that you use for real data transmission instead of calibration. And this is why a 40 MHz channel is more than twice as efficient as a 20 MHz. Twice because you double the size, but more than twice because you also reuse some channels that were just used for nulling to isolate or locate the middle of band and pilot to know the noise figure. But this comes with a cost. I'll come back on that in a few minutes. When you move to 80 MHz, well, basically the same thing happens. You take two 40 MHz, you squeeze them together, and now we have a large 80 MHz channel. You still have 6 channels set to null at the bottom and 5 set to null at the top to isolate the transmission from neighboring channels. And with the same logic, we're going to remove the empty 3 that we have in the previous middle of the 40, and we're going to use those for transmission. And we're going to use the 5 and 6 at the edge of my 40 MHz channels before, and only use 3 of those to identify the middle of the wave, the middle of the transmission. So the result is that the 80 MHz transmission still has 6 plus 5 plus 3 channels that are set to 0, those black ones. But as you're using two 40 MHz transmissions, that makes that from 40 to 80, you still have 14 subcarriers set to 0, so that means that one of the 14 that you had before are now used for transmission. 14 subcarriers that you take from the previous middle transmission and partly from the edge to transmit more data, and that's going to make 80 MHz more efficient again than 40 MHz, and more than twice more efficient because you have 14 new channels that you can reuse there. The same goes for the pilots. Before, we had 6 pilots on each of the 40 MHz transmissions, and here again the temptation is to say, do I still need 6 and 6? And the answer is maybe we can do with 4 instead of 6. So from 6 plus 6, we move to 4 plus 4 on each half of the transmission, and now we have 8 subcarriers left for the pilots instead of 12. Now your pilots represent 3% of the transmission, and this altogether makes that your 40 MHz transmission is 2.15 less efficient than your 80 MHz transmission, because the 80 MHz has more channels that we use for data. As a side note, when you move from 80 MHz to 160 MHz, we do not undergo the same process. In other words, we just keep the 80 MHz channels as they were, and we just stick one 80 MHz channel to another 80 MHz channel, and voila, that's your 160 MHz channels. We're not going to change the pilot numbers, we're not going to change the subcarriers to reuse some of the old flattened null channels. We're just going to stick to the 80 MHz channels as they are and just put two next to each other. The result is that, by the way, you can have a transmission in 160 MHz that is not a large 160 MHz channel. It can be one chunk of 80 MHz and another chunk of 80 MHz somewhere elsewhere in the band. Those two 80 MHz channels do not need to be continuous because you're basically using 80 MHz each time independently, so they can be far apart if needed. So here again, we still have these 3% pilots and basically twice as much transmission as in AT because we're just using AT channels twice. This is interesting, of course, because if you look at the band in 5 GHz, there is not much space for a one large 160 MHz transmission. It's probably easier to be able to set two 80 MHz channels and put them apart from each other. That would be simplifying the allocation of band. But back on the channels, if you look at what we've been doing, every time we've been changing from 20 MHz to 40 and to 80, we've done two things. Reduce the number of null channels on one side, and also reduce the number of pilots on the other side. This is great on paper because it allows for more channels used for data transmission. But every time you reduce the number of pilots, what you also do is lessen your ability to know what the noise figure is between those pilots. So if you look at my light wave here, I know very well what the noise figure is around that red pilot in the neighborhood because I have the pilot to tell me and compare what I should receive with what I receive and know the noise figure for this area. But if I look right in the middle of my 80 MHz bottom half, I'm pretty far from the pilots at that area. Therefore, if there are some narrowband interferences in the neighborhood, I may not be able to understand what the interference figure is, what the noise figure is in this frequency range simply because there is no pilot to tell me. Same goes here and same goes there. So you see, every time we increase the size of the channel, we also decrease the number of pilots, and as a consequence, we also decrease our ability to know the noise figure. What is the consequence of that? Well, the consequence is that if you want to use an 80 MHz wide channel, you need to have a signal quality good enough that you can do without knowledge of the noise figure between those pilot frequencies. In other words, if you have a lot of noise in a 20 MHz transmission, you have enough pilots to have a good understanding of this noise figure throughout the 20 MHz transmission. But if you have the same noise in an 80 MHz transmission, well, now you have areas in your communication where you don't have a good understanding of the noise figure. And maybe the noise is not the same as the one in this area. And if it's the case, your assumption for the noise here, which is built on the knowledge of the noise in this area and that area, is simply wrong. The result is that you're not going to be able to receive this area well enough to understand what is being said. So what does that mean for your transmission? Well, that means that in the 802.11 AC amendment, there are some minimum performance figures that vendors must comply to. That is to say, what kind of signal do you need and what kind of signal quality do you need to be able to receive a transmission in 20 MHz, 40 MHz, 80 MHz, etc. Those are minimal performances and most vendors do better. Cisco does much better. But what is interesting is that the same logic will be seen in the theoretical minimum receive sensitivity and in the vendor practical performances. They may be better, but they follow the same logic. And that logic is that if you look at a 20 MHz transmission, for example, for one special stream, you need a minimum signal of minus 76.5 dBm, and you need a minimum signal-to-noise ratio of 17.5 dB. That is to say, your useful signal must be 17.5 dB better than the surrounding noise. With 17.5 dB, you can know what is being sent. But if you look at the same table and you look at the 80 MHz line, so this is the same one special stream transmission, but this time you're using an 80 MHz wide signal instead of a 20 MHz wide signal. Of course, your speed will be much higher, more than 4 times more than 20, because we reuse some channels. But the other consequence is that you need a stronger signal, minus 71.5 dBm, where you only need minus 76.5 dBm for 20 MHz. You need not only a stronger signal, but it has to be also of higher quality, 22.5 dB over the noise figure. In other words, if you and I sit next to each other at the same distance from an access point, and I'm using a 20 MHz wide channel device, and you are using an 80 MHz wide channel transmission, with only 17.5 dB SNR, I can read the signal. But at the same location as I am, with your 80 MHz transmission, you just cannot read it. You have to get closer to the access point to get a stronger signal and to get a stronger SNR. So although it seems that as you increase the size of your channel, you also increase the performance of your device, which is true, it is also true that you also reduce the size of your cell. Every time you double the channel size, it means that to get the same modulation, the same transmit performance, you have to get a little bit more signal than you had with a smaller transmission. And that means that every time you double the size of your channel from 20 to 40, from 40 to 80, you reduce your cell size because you have to get a bit closer to the access point to get the same performances you had with a narrower channel. The same goes, by the way, when you increase the number of special stream. The top of the table shows one special stream transmission, and the bottom 3 special stream transmission. And you can see that every time you add one special stream, you send another signal in the same frequency, and your receivers are going to distinguish one transmission from the other. So it looks like you're going to double the capacity, double the speed, and triple if you use 3 special streams as you see here. But another consequence of that is that you will need a higher signal altogether so that your receiver is able to isolate one from the other and deduce one from the other. And the larger your transmission, of course, the more signal you need. So just like for the channel size, the special stream can be misleading. It looks like by just adding a special stream on your client receiver or on your AP, you simply double the speed of your cell. It looks like this, and this is true, but it also reduces again the size of the cell, because to get the same speed, you also have to get more signal, so it means that you have to get closer to the access point. Think about it for your design. If you set your channel to 20 MHz and you test during your site survey one special stream, you may find the cell edge at a point where you can have only 17.5 dB SNR. And you think that this is the size of your cell, this is where you'll get this 20 MHz wide, one special stream, 65 megabit per second transmission because you're using MCS7 there. And you can think that this is where MCS7 stops, and this is all the way up where you can get MCS7. Well, that may be true for 20 MHz, but if you configure your access point for 80 MHz and more than one spatial stream, that point is not the edge of your cell anymore. You have to get much, much closer to the access point to get the same MCS7 with a larger transmission and more spatial stream. So the conclusion is, when you design your cells, you should use the modulation, but also the number of spatial streams and the channel width that you plan on using in real deployment, because those two parameters are going to dramatically change the size and maybe the shape of your cell. I hope this was useful for you, and I'd like to thank you for watching.